The LEO SAR satellite system uses Doppler processing to generate a beacon location. The LEO SAR system consists of two segments: the space segment, low altitude Earth orbit, or LEO satellites, that detect activated distress beacons, and the ground stations, called LEOlets, that receive the beacon signal from the satellites and use Doppler shift to calculate the position of the activated distress beacon. The LEO SAR system can also record any position encoded in the beacon's message, as provided by the global navigation satellites, such as GPS. Here's how Doppler shift works. As a LEO SAR satellite approaches the activated distress beacon, the frequency of the signal received by the satellite appears to be at a higher frequency than the signal transmitted by the beacon. Then, as the LEO SAR satellite is at its closest point to the beacon, the frequency of the received signal is equal to the transmitted signal. Then, as the LEO SAR satellite moves away from the beacon, the frequency of the received signal appears to be lower than the frequency of the transmitted signal. When the received frequency is plotted over time, the result is a Doppler curve, which gives us a Doppler position. A LEOlet needs to detect at least 3 beacon bursts to compute a Doppler position estimate. With each LEO SAR satellite pass over the activated beacon, the LEOlet produces 2 position estimates for each beacon detection, often called the A and B position. One will be close to the correct beacon location, and the other will be its mirror image, which is the reflection of the correct location on the opposite side of the satellite's ground track. The LEOlet uses the fact that the Earth is rotating below the satellite, producing another small Doppler shift, to estimate the probability that each of the 2 positions produced is the correct location of the beacon. The LEOlet cannot always correctly identify which position is the real beacon location based on one LEO SAR satellite pass alone. The MCC must wait for a second independent position to be provided by another satellite source before it can resolve the ambiguity of these 2 solutions and identify the correct beacon location. Some of the key parameters that are used to define the Doppler curve and the independent position estimate that is generated by the LEOlet solution processing include time of closest approach, TCA, and cross-track angle, CTA. The time of closest approach, TCA message field number 14, shown on the screen here, is the time when the satellite passes closest to the beacon, which is identified using the inflection point in the Doppler curve. The cross-track angle, CTA, message field number 17, shown here, is the angle measured between the satellite and the beacon from the center of the Earth through the TCA. It is important because if the CTA is close to 0, this means the satellite has passed directly over the beacon and the 2 positions calculated by the LEOlet will be very close together. Kospa Sarsat, we save lives.